Welcome.
Welcome to Lab 5.
Lab, yeah, 5.
Inclined planes. Here we have the base of our triangle here, where beta would be right here, and we are going to measure the opposite side. Yeah, this is our hypotenuse, and we would measure the opposite side to find sine of theta to get our theoretical acceleration.
Usual. So we turn it on. It's gonna be our work. Graph.
Do we present
got
the
two.
What? You guys present the equipment?
Yeah. We take your job.
I saw.
How much grams is this one?
Taking a shit is like that.
This one is
Frankly,
200.
when it comes to velocity, how hard it impacts.
And it is about
100.
100, so 50 each. So 50 each. Nah.
It goes.
So we actually moved the motion sensor to the middle because it wouldn't read. It wouldn't read from all the way over there, so we moved it right here in the middle. And now we got perfect reads, perfect graph. Yeah.
That's smoother than last time.
Smooth view, yeah.
Are we expecting acceleration to increase? Yes. As we increase the weight and we increase the incline, the acceleration should increase with each change. As the weight changes, pulling it down harder, acceleration should be higher. With the higher incline, there should be a stronger force pulling it down, increasing the acceleration as well. Both of these will increase the speed and the acceleration as it goes down the hill. Compared to our plane or normal versions, there would be a noticeable difference. Are we expecting a different percent error? Not necessarily. The percent error should stay within a certain range. Currently, if we have, just as an example, if we have a 15% error, should stay within that certain area. It shouldn't jump to 40, it shouldn't be 0. We use the same materials, being the rail, air compressor, sensor, computer, and the sensor plate itself. Since everything stay consistent besides the variables that we're changing, there should be no dramatic change in percent error. If there was to be a dramatic change in percent error, our calculations could have been incorrect in the way we perceived it from the computer, the weight that we measured themselves, or basic human error through the math equation.
problem solvers here.
This we got it.
That's what 100 grams is stopping. You know.
I was gonna stop, keep recording until.
We're good. Change.
I'm gonna stop it after.
Today we're reporting on our physics experiment studying acceleration on an inclined plane. The goal of this experiment was to compare the acceleration measured experimentally with the acceleration predicted by theory. In physics, the acceleration of an object moving down a ramp depends on the component of gravity acting along the incline. This relationship can be described by the equation shown here, where acceleration equals gravity multiplied by sine of the ramped angle. Using our ramp measurements, we calculated a theoretical acceleration of about 1.2 meters per second squared. We then conducted several trials to measure the actual acceleration of the object moving down the ramp. In the first trial, using a mass of 50 grams, we measured an acceleration of 0.365 meters per second squared, which resulted in a percent error of 77%. In the second trial, with 100 grams, the measured acceleration was 0.21 meters per second squared, which produced a percent error of 87%. In the third trial, we measured the acceleration. The measured acceleration was 0.1475 meters per second squared, resulting in an even larger percent error of 89.8%. Overall, the experimental accelerations were significantly smaller than theoretical acceleration predicted by the equation. When we compare the results, we can see that the experimental acceleration are clearly different from the theoretical acceleration. The measured values are much smaller than the equation predicts. However, this difference is actually expected. A theoretical model assumes ideal conditions, meaning there is no friction, no air resistance, and perfect accurate measurements. In our real experiment, these conditions are not possible. One major factor is the friction between the object and the ramp. Although we have air pumping through it, and it's supposed to be non-frictionless, there is still some friction present. Air resistance may also have a small effect. Additionally, small errors in timing and velocity measurements could affect the calculation of acceleration. Another factor could be slightly differences in the ramp angle or inconsistencies when releasing an object. Even small variations in these conditions can influence the results. Because each trial had slightly different conditions, the percent errors were also different between trials. This is normal in experimental science because measurements are rarely perfect and consistent. In conclusion, our experiments show that while the theoretical model predicts the acceleration based on gravity and the ramp angle, real forces like friction and measurement limitations can cause the experimental results to be lower. This demonstrates the difference between ideal physics models and the real experimental conditions. Thank you.
These are our numbers for lab 5. First row, we have where we calculate the theoretical acceleration. Then second row, our theoretical acceleration is 1.6174 meters per second squared. Our second row is where we tested it first with the 50 grams, our first set of weight. And our experimental acceleration there was 0.365 meters per second squared with a percent error of 77.43%. Then we went to the 100, we upped the weight to 100 grams. Our experimental acceleration there was 0.21 meters per second squared Our percent error was 87%. Then the last one, we changed the angle. We lowered it by a meter. Our theoretical acceleration for that was 1.448444 meters per second squared. And the percent difference from the first one was 10.44%. Then we tried out that one. We tested it out. Our experimental acceleration with that one was 0.1475 meters per second squared. And that one gave us a percent error of 89.81.
The experimental acceleration with the most significant percent error was experimental acceleration 3, which had a percent error of 89.81%. This was the highest error compared to the other trials, which had errors of 77.43% and 87.01%. Because this value was the farthest from the theoretical acceleration of 1.44844 meters per second, it is considered the most unexpected result. This large difference suggests that experimental factors such as friction, measurement timing, or small setup errors may have affected the results during the trial.